Welcome to this lecture on AI community tools, Python, TensorFlow/Keras, PyTorch, and web scraping. Today, we'll explore how these tools form the foundation of modern AI systems, especially within biomedical and global health applications. And this lecture will give you the practical intuition and technical confidence to navigate this ecosystem effectively. By the end of this session, you will 1. Understand the core software tools used for AI and machine learning, Python, TensorFlow, PyTorch, and Keras. 2. Learn how to access and build relevant datasets for research. 3. Gain an introduction to web scraping, an essential skill for ethically collecting and structuring data from the internet. Our focus will be on practical understanding, clarity, and reproducibility, the cornerstones of responsible AI for health. Let's start with Python, the universal language of data science. Python is a high-level, it's a general-purpose programming language known for readability and community-driven development. Its simplicity, open-source nature, and flexibility have made it the default language for artificial intelligence today. Python's roots can be traced to older numerical languages like Fortran and C, but its design philosophy prioritizes human readability. If you've used MATLAB or R, you'll find Python intuitive. What makes it extraordinary is its massive ecosystem of libraries, built by and for the community. Some key packages include NumPy for numerical computing with arrays and matrices, Pandas for handling structured datasets, SciPy for scientific and statistical analysis, -matplotlib, and Plotly for visualization. Together, these make Python a complete scientific computing environment, empowering researchers to prototype and scale machine learning ideas efficiently. The Python ecosystem works in layers of abstraction. At the core lies the Python language itself, the interpreter and standard library. On top of that, scientific libraries like NumPy, Pandas, SciPy, and Matplotlib provide tools for computation and visualization. Then come the higher-level machine learning libraries, scikit-learn, TensorFlow, PyTorch, and Keras. scikit-learn covers classical algorithms, regression, clustering, PCA, and cross-validation. TensorFlow and PyTorch enable deep learning and neural network training. Keras sits even higher, offering an elegant, user-friendly interface to both TensorFlow and PyTorch. This modular structure allows beginners to start with simplicity and experts to dig deeper into customization. Jupyter Notebook is the laboratory notebook of data science. It allows you to make and document executable code, text explanations, and outputs, all in one interactive environment akin to a laboratory notebook. Jupyter Notebook and Jupyter Lab was originally designed for documentation and visualization, but it has evolved into a cornerstone of reproducibility in research. Google Colab builds upon Jupyter by hosting your notebooks in the cloud, giving you free access to computing resources, including GPUs and TPUs. Each notebook.ipnb file runs in a managed Linux environment with Python and common ML libraries pre-installed. You can even mount your Google Drive directly to access files, making it one of the most accessible tools for training models anywhere. Let's now examine the 3 key frameworks that dominate modern machine learning. TensorFlow, developed by Google, is an open-source library for numerical computation and large-scale machine learning. It uses so-called symbolic computation graphs to represent and optimize data workflows, making it highly scalable across CPUs, GPUs, and TPUs. PyTorch, developed by Meta's AI Research Lab, focuses on dynamic computation graphs, meaning the model structure can change as it runs. This flexibility has made it the preferred choice for academic research and rapid prototyping. Keras began as a high-level interface for TensorFlow, but has evolved into a unified API that now supports TensorFlow, PyTorch, and JAX backends. Its design philosophy, simplicity, modularity, and speed of experimentation. So how do they compare? Ease of use. Keras is the simplest, ideal for beginners and quick model prototyping. Flexibility. PyTorch allows the most customization, making it ideal for novel architectures and experimental research. Performance. PyTorch is generally faster, though TensorFlow is catching up with continuous optimization. In practice, professionals often use all 3, switching depending on the project's complexity and goal. TensorFlow for deployment, PyTorch for exploration, and Keras for simplicity. Here's a quick code comparison. Both frameworks start by importing libraries and defining layers, optimizers, and loss functions. Keras lets you build models in just a few lines, using its sequential API. PyTorch, on the other hand, requires defining a custom neural network class, explicitly handling forward passes and gradients. The main takeaway: TensorFlow/Keras abstracts complexity for productivity. PyTorch exposes it for flexibility. In real-world AI, the best engineers are bilingual, or even trilingual, in frameworks. Whether working in academia or industry, you'll encounter teams using TensorFlow, PyTorch, or both. As of now, TensorFlow remains dominant in production and mobile, thanks to TensorFlow Lite and TensorFlow.js. PyTorch leads in research due to its intuitive debugging and flexibility. Keras is the bridge that connects both worlds, making experimentation fast and seamless. TensorFlow comes with powerful tools that extend beyond model training, such as TensorBoard for interactive visualization of metrics, losses, and network architectures, TensorFlow Lite for mobile deployment, TensorFlow Federated for distributed, privacy-preserving learning, and TensorFlow Hub for sharing and downloading pre-trained models. Keras complements these with simplicity, modular design, and community-driven resources. Keras 3.0, for instance, provides seamless interoperability across TensorFlow, PyTorch, and JAX. Now that we have talked about Python and ML-specific packages, I want to make a brief note about code that further facilitates the exploration of datasets and machine learning systems, such as LazyPredict. LazyPredict is a handy Python library that fully automates the training of multiple classical machine learning models with just one line of code. It's perfect for establishing quick performance baselines before diving into deep learning. Tools like this, and there are many of them out there, can help you save time, focus on data preparation, and identify promising algorithms early. Great. Now, since data is the fuel of AI, including in health applications, data access needs to be considered seriously, and particularly in healthcare, where there are important, strict ethical and privacy constraints that should be followed. Please make sure that you have the right permissions and consent to use any data you find or attempt to use. Some reliable sources of data for machine learning applications in healthcare include Kaggle, a global platform for open data science competitions and datasets, and the National Institutes of Health, NIH, and National Library of Medicine, which host extensive public repositories of biomedical images and records. Finally, GitHub and institutional repositories, where researchers typically share datasets and scripts openly whenever possible. Remember, always ensure data use complies with privacy laws, HIPAA, GDPR, and Institutional Review Board guidelines, as that will make it all easier for you downstream when it's time to document results, publish, or deploy systems in the real world. When public data is limited, researchers often build new datasets. This involves 3 steps: primary data collection, gathering new observations under IRB-approved protocols; secondary data aggregation, combining open datasets or augmenting existing ones; curation and metadata creation, labeling, cleaning, and documenting for reproducibility. A well-curated dataset is often more valuable than a model itself. It can drive innovation for years. Now let's discuss web scraping, the automated collection of data from websites. Ethical scraping means respecting site terms of service and intellectual property rights. The goal is not to take private information, but to extract publicly available, structured data for learning purposes. Some useful tools include Beautiful Soup, Python library, great for HTML parsing and simple scraping; Octoparse, a user-friendly visual scraper for structured data; Scrapebox, an advanced high-volume scraping platform; ParseHub, fMiner, and DataMiner, browser-based or hybrid solutions. Each serves different purposes, from lightweight experiments to large-scale data collection. Imagine you are building an early diagnostic tool for anemia detection using smartphone images. You might need thousands of photos of nails, tongues, palms, and conjunctiva, labeled as anemic or healthy. A web crawler can systematically search for images that fit these categories, download them, and organize them into category folders. Once cleaned and verified, this data could train a prototype model to predict anemia, a concept that could transform maternal health screening globally. In summary, today we covered the Python ecosystem and its scientific libraries, the 3 core ML frameworks, TensorFlow, PyTorch, and Keras, key methods for accessing and aggregating datasets, the fundamentals of ethical web scraping. These tools together empower you to move from idea to prototype quickly, and to do so responsibly, transparently, and reproducibly. Thank you for your attention, and remember, AI in health isn't just about algorithms, it's about curiosity, collaboration, and ethical innovation.